Hello everyone, welcome to the episode 2 of Transformer Slam Learn With Me series. In the last episode we went through some basic PyTorch tutorial, and in this episode we will try to make a CNN manually as described here in the plan PDF. But before we get into that, I would also suggest you all to go through these other tutorials, tensors and datasets and data loaders, to get more idea about it, even transforms maybe. But yeah, going ahead, we'll try to create a CNN today, and let's jump into the Colab notebook. I am going to follow this tutorial today. First of all, we'll import everything. Now we will specify the system device, whether it's going to be CPU or a GPU. So if GPU is available, it will take GPU. Okay. Um, okay. So as we had seen in the first episode, looks like the neural network again that we're going to make will be inheriting from nn.module. Okay, and let's try to recall. Similar to the first video, this is again creating a 5-layer neural network with ReLU activation, alternate ReLU activation, and similar to the previous one, it has a forward function that returns logits. Let's run this. Okay, and we put the model to device here. Okay, similar, very similar to what we had done in the last session. Okay, so we are going to copy this into our notebook and we run it. So I did not know very well what this is doing, so I asked ChatGPT to help me a bit. And what it says is this one here is creating a tensor of size 28 cross 28 cross 1, basically creating a dummy data where all the 28 cross 28 is populated by a random number. This is doing a forward pass of the model and getting the logits. Here, here we are applying softmax to dimension 1, the logit tensor that we have got, and then we are getting the predictions. So going back to ChatGPT for an example, this is like example of what is happening. So for an example, this is the logits that you are getting for each classes 1, 2, 3. If you convert it to softmax, that is into a probabilities of 0 to 1, the maximum that we see is of 0.87, and thus the class predicted is 2. So that's what's happening here. We ran it already. Now layers. Okay, here are some experimentations that we can do with the layers to know more about it. So let's go ahead and see. Okay, so we are creating again dummy data of random numbers, but this time the channels is 3. So this dummy data assumes that this is an RGB image, so 3 channels, 28 cross 28 size, again all of it populated with random numbers. So with image.size, this is what we get. Flatten. So I believe we are going to flatten it out, so it will become a single one-dimensional vector. Okay, so this remained 3, and 28 into 28 we got 784, but this remained 3. I wonder why that is. Let's ask GPT again. Okay, so GPT tells me that when we flatten, the first dimension, whatever it is kept as it is, and the rest is flattened. So that's why we get a 3 comma 784, and that is because by default flatten expects that the first channel will be batch, and it makes sense to not flatten out the batch size, right? So each individual data point in the batch should be flattened, not the whole batch. So it makes sense. So usually, like for example, if you have a batch of 64, so this is what you would be flattening, something like this. So it will be 28 into 28 into 3, and 64 will remain as it is. So that's how it normally happens. Uh, okay, let's go ahead. Linear. Here we are creating a layer of a fully interconnected layer. Um, Applies a linear transformation on the input using its stored weights and biases. Okay, I don't know where those weights and biases are coming from. We'll see about it more later on. But anyway, so the flat image that we created here of the shape 3 comma 784 is created as a hidden layer, and since the out features is 20, I think I made a mistake here. um, okay, let's see what this does. Okay, so ChatGPT tells me that what we discussed earlier, this particular line is creating a fully connected dense layer, and it is defining that the input will be 28 cross 28 and the output will be 20. So what's happening here is, you can see, um, each so here each sample, or each feature, sorry, in the from the input layer is finally getting transformed into a 20 feature output. So that's what the hidden layer is doing. Right, each input sample gets transformed into 20 element feature vector. So what this is doing is, it's mapping a 784 dimensional input to a 20 dimensional output. Okay, um, so from what I got to know about this is, nn.linear creates a dense layer where it will be a fully connected layer, and it depends on you how you want to use it. Like for example, here we see that in features is 784 but out features is 20. So that means this layer will have 20 nodes, but it will be taking inputs from, it will be taking 784 inputs, which will be coming from the first layer of uh, input, which is basically the flattened out image, right? So that's how in a way it is defined that okay, this will be the first layer, because we know that our input is 28 cross 28 and we want it to give 20 output. So yeah, so suppose you are creating this kind of network. Okay, so this particular one, this layer, suppose this layer, right? How many inputs is it taking? It's taking 1, 2, 3, and then this one is taking 1, 2, 3, this one is taking 1, 2, 3. So the inputs that are coming are 9, and the outputs that are going are again 1, 2, 1, 2, 3, 1, 2, 3. So I believe 8 outputs, right? So the input for this is 9, 1, 2, 3, and the output is 8, right? So for this layer, if we have to define this layer in this way, we are going to define in features as 9 and out features as 8. But similarly, we know that our input flattened out vector is 784 size, and suppose we want this one. So this is a fully connected layer. This one was not a fully connected layer because we saw that this and this is not directly connected, as in this one, this and this. So for this, if we want to define, this will be a fully connected layer. Suppose we have 784 inputs, so 784, and the out will be 9. So I hope maybe you did not get a complete clear idea, but I hope it helped the explanation. But anyway, moving on. So that's what this is doing. Okay. Anyway, moving on. ReLU. Okay. So now that we have our layer, next will be the activation layer. Let's run this and see. Okay. So here are the values before passing through ReLU activation layer. Here are the values after passing. Also, it's good to notice how we are actually passing the info from one layer to another. So nn.relu, and then not within this bracket, but after that we pass the hidden previous layer. Okay, and then we are just renaming hidden one again. So we see the ReLU activation happening, and what this does is it kind of normalizes everything between 0 to 1. So here we see negative values, probably might even be some values above 1. I don't know, I don't see any values, but anyway, we have negative values and positive values here. This kind of normalized it all to values between 0 and 1. So that's what ReLU activation does. Now moving on ahead, sequential. Okay, so sequential, this is another way of defining how your model can look like layer by layer. So you can define, suppose we define that the first layer is going to be the flattened out layer, and then the second one is layer 1, layer 1 that was defined here, right, with in feature 784 out feature 20, and then we have our ReLU activation, and then we have another linear layer that has input 20 features, output 20, output 10 features, right? So this kind of overall defines how our model looks like. So this model has 1, 2, 3, 4, 4 layers, and the data passes in sequential order how these layers are defined. So passes to this first, this second, sorry, this third, and this after that. Flatten, let's just want to go back to flatten and see what it was. Here is where we define flatten and what it's going to contain. But anyway, so yeah, the nn.sequential is basically a convenient way to create your model layer by layer and make it in customized manner. So okay, so here in the last two lines we are passing a dummy data and we are getting the output logits. Okay, now softmax. Okay, so softmax, as maybe many of you might know, uh, it's commonly used as output layer because it uh, whatever your logits outputs you're getting, it makes it into probabilities of different classes. So let's run this, and we have our probabilities. Let's print the probabilities and see what it is. Okay. Okay, so this, it, as I mentioned, so here instead of taking 3 for the RGB channels, it has taken this. I mean, that's how it normally is. Earlier it was a bit confusing, so sorry if you got confused earlier. Even I was not really sure, but so what I understand is this torch, when you are creating anything, not just when you are creating, when you are passing anything to the model, if it is a tensor, the first value of the tensor is taken as a batch. Okay, so that's why what we see here is we are actually getting 3 outputs, 1, 2, and 3. So it's treating it as 3 batches, and we saw that the last layer output was 10. So what the model understands is it has uh, it has to classify this particular data point into these many classes: 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And what are the probabilities of the this particular data 1, belonging to each of the class, right, by doing the softmax, right? So that's what you see here is, so if we see for this one, I think it's getting the highest probability for this 0.1184, or no, on this 0.1190. Okay, so this model would predict that this data point belongs to this class because it has the highest probability. Okay, so that's how it is. Now moving on. Okay, so what this is telling is, if you define your model with nn, like your suppose your model is a subclass of nn dot module, it's inherited from nn dot module, then by default you will have access to parameters, right? So that you can, observe or make changes to those parameters. It automatically tracks all fields defined inside the model object and makes all parameters accessible using models parameters. Okay, so let's see what it says for our model. We have the biases. Okay, I think I still need to learn a lot to understand what each of these are. A lot of things are still not clear. I would want to understand how it works when the outputs are not classes. I mean, when it's not a classification problem as such, it could be like any kind of problem, right? It could be regression problem or something else, right? So I would like to understand how that works out. But anyway, yeah, I think we'll get to know all that as we move ahead in the series. This video is going longer than I expected. So far we have seen about creating neural networks in detail, more in detail compared to what we saw in first episode. But still we haven't moved on to creating convolution neural networks with convolution layers. So I'm thinking I'll break down this episode into two parts. In the next part, we will see how to create convolution neural networks. And for this part, this is about it for now. So thank you. Stay tuned.